right, welcome back. I hope you had a restful break and just pat yourself on the back because we are over halfway through with calculus. Yay! There are 9 sections in our book and you have already finished 5 of them. So we are getting there. We've covered the 3 big ideas of calculus, which are derivatives, integrals, and limits. So we're going to use a lot of things just to apply that stuff now. So enjoy! So today we're going to talk about the second fundamental theorem of calculus. And what you might think is, wait, didn't we already learn a fundamental theorem of calculus? You are correct, we did. This is the fundamental theorem of calculus. This is the mathy way that we write it a lot of times. Basically what this says is if I have some function f, I'm going to call it little f, and I know the big F and the little f is a little confusing, so I have a little bit easier way to show it in a minute. If we have some function f, and we know that the function f is here, right? The next function up in the totem pole is big F. Then to evaluate the definite integral, what I could do is I can find the antiderivative, which would be big F, and I would evaluate it at B and subtract the evaluation at A, and that's the fundamental theorem of calculus as in a nutshell. Let's look at that a little bit easier way to think about it. So this is the way I like to think about the fundamental theorem of calculus. Might not be quite as like the mathy way, but it helps. So think about, we have this function here, and we know that it's just, it's this function f prime of x, right? It's just some random function. We don't necessarily need to know f of x. So here's this function f prime of x, and we want to find the antiderivative of it, which is the integral from a to b. That means we're going to take this function, we're going to step up one step, right? And we're going to, of course, if we step up one from this, we're going to get f. And then we just evaluate it from b to a, so we take f of b minus f of a, and that actually tells us the area under the curve for this specific function, right? So that's the fundamental theorem of calculus. Now, let's find out what the second fundamental theorem of calculus says. So first I want you to remember that if we take the derivative of an integral, they basically like cancel each other out because they're inverse operations from each other, right? So if I have some function here, this is the function, and I take the integral, I move up one step, right? And then I take the derivative and I move back down to the exact same place, right? Or if I'm here at some function and I take the derivative, I move down a step, and then I take the integral, I move up a step, right? That's really all I'm doing. So I take a function, I integrate, and then I differentiate, I end in the same place, okay? That's all that this is saying. So let's look and see what happens when we have definite integrals, because a definite integral is a little different because it's talking about not the function as a whole, it's talking about a specific area under a curve. So first, let's just integrate this. It says the integral from 0 to x of 2t minus 3 dt. So we know from the fundamental theorem of calculus that that I have to go up a step, right? I have to integrate. So that would be 2t squared over 2 minus 3t evaluated from 0 to x. Okay, and obviously those 2's divide each other out, and I have t squared minus 3t evaluated from 0 to x, which equals x squared minus 3x, right? That is f of x minus, and then we have to do f of 0, right? So this is the fundamental theorem of calculus, says we evaluated at x, and then we evaluated at 0, and our luck would have it that f of 0 is simply 0. So we just subtract 0 from that, and there you go. That's the derivative from 0 to x of 2t minus 3. Do you notice something about that? We kind of like got rid of our t, right? Like t just disappeared and now we have x. It's like we took one variable and we just like put in another variable. So let's look and see how that relates. So over here it asks us to find the derivative of the integral. Well, we actually just found that integral, right? We just found this entire thing is right here, right? those are equal to each other. So when I'm looking for the derivative, I'm looking for the derivative of x squared minus 3x, correct? Because I just found out what the integral of 2t minus 3 dt is, right? Okay, so I'm finding the derivative of this. So the derivative of that is 2x minus 3. Huh. That sure is interesting, because when I look back over here, 2t minus 3, I took the integral, and then I took the derivative, and ended up with 2x minus 3. So it's like basically the same function, but I just put x in there, right? Okay, let's look at one more to see if it works like that every time. And you could probably guess that it does, because, you know, you guys have been in math long enough to play the what is the teacher thinking game. So let's take a look at this. Here's some function f prime of t. We're going to find the derivative, or the integral from 10 to x. So we know that if we have f prime of t is here, we're going to go up one step. So that's going to be f of t evaluated from 10 to x. And so because of the fundamental theorem of calculus, we know that that's f of x minus f of 10. So f of x is f of x, and f of 10 is f of 10, because we don't actually have a function here, we just have a function, like we just have function notation, so we don't really know what the actual function is. So we know that the integral from 10 to x of f prime is this, okay? And look, we have that over here too, don't we? So everywhere we have that, we can just put f of x minus f of 10. Okay, and then it asks us to find the derivative, d dx, that's what that means, remember? The derivative of f of x minus f of 10. Well, here's what's super important to remember. F of 10 is a constant, because it's some function, any function, we don't know what the function is. It could just be something simple like x squared, or it could be something super complicated, you know, like cosine, cotangent, blah, 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 of 10, right? But when you plug in 10 for every variable in a function, every number in that function becomes a constant, right? It doesn't matter. It might be a weird constant, but it's still a constant, right? It could be any number. So f of 10 is a constant, and that's super important to remember. This is a constant. So let's take the derivative. Well, the derivative of f of x would be f prime of x, correct? Okay, and the derivative of a constant is 0. So the derivative, excuse me, the derivative of this definite integral is just the function that was inside the definite integral with x instead of t, okay? And you notice that it doesn't really matter if this was 10 or 0 or anything else. This right here becomes 0, even though, like we put in 10, right? Because it's a constant. So that's what the second fundamental theorem of calculus tells us, is that when I take the derivative, if I have, okay, let's start with this. If I have constant a, and I take the derivative of a definite integral from a constant a to some variable, then this whole mess is going to equal the function with x instead of t, okay? Because I'm going to take this function at t, right? I'm going to integrate it. Whoop, I'm going to evaluate it, and then I'm going to derive it. And what's going to happen is I'm going to come right back to the same function, but instead of having t in it now, I have x, because that's where I evaluated it at. So it's really just like plugging stuff in. So let's see what happens when you have something like x squared. Now you're going to see that this wouldn't, if this x was just some constant, then we wouldn't even be talking about this, because if you can look up here, let's think about it. If this number was 15 instead of x, then I would have f of 15 minus f of 10, right? Well, f of 15 would be a constant, f of 10 is a constant, and the derivative of a constant minus a constant is 0. So if we're talking about a definite integral with constant limits of integration, we don't even worry, right? Like if we had like the derivative of a definite integral with constant limits, then it's just 0. But we're talking about the derivative of an integral, and this integral has another function inside of it. And you'll notice that t just kind of disappears. We call it our dummy variable. It's a variable that really doesn't matter. It doesn't even matter what that number is or what that variable is. We just kind of use it as a placeholder until we end up evaluating for x. So let's see what happens if it's more than just x, maybe another function of x, but like x squared. So let's think. Okay, so our first thing we're going to do is we're going to take the derivative, or the integral, sorry, of this derivative. So the integral of some function f prime of t would be f of t, and we would evaluate it from 0 to x squared, which the fundamental theorem of calculus tells us that's f of x squared minus f of 0. Okay, so we know what this is, and we see it right over here, right? That exact expression. So we want to take the derivative of f of x squared minus f of 0. Now remember, since f of 0 is a constant, when we take the derivative of it, we get 0. So really, we're just taking the derivative of f of x squared. So you'll notice that this is actually a chain rule issue, right? I have the outside function is f of x, and the inside function is x squared, right? So I have an issue here where I have a function like the chocolate on the outside and then the peanut on the inside, right? So when I derive this, when I take the derivative of this, I end up with the derivative of the outside. Let me see if I can get the right color that I want. Okay, so I end up with the derivative of the outside with the inside still intact times the derivative of the inside. So that's the chain rule, right? When I take the derivative of some function, I end up with the derivative of the outside with the inside still intact times the derivative of the inside. So this is this whole mess evaluated. And if you'll notice, it's basically the same thing, right? We plugged in x squared where t was. The only difference is we had to tack on the derivative of the inside because this is a chain rule. So let's see what happens when we have a function. We have a couple functions. Okay, for our limits. So let's find the derivative or the integral of this first, right? So this would be f of t evaluated from x cubed to 2x, which equals, from the fundamental theorem of calculus, f of 2x minus f of x cubed. Okay, and then we see this right here, right? We evaluated that already. So now we're going to find the derivative dx of f of 2x minus f of x cubed. So the derivative of f of 2x would be f prime of 2x, right? The derivative of the outside with the inside still intact times the derivative of the inside. Okay, then we're going to subtract. Let's find the derivative of f of x cubed. That would be the derivative of the outside with the inside still intact times the derivative of the inside. And actually, we could just leave it like that. That's our answer. So you see what we did is we plugged in these limits of integration here. We plugged in 2x and we plugged in x cubed, but then we had to tack on the derivative of the inside for the chain rule.